Hey everyone, this is Edwin Hernandez and this is my video for lab 4. In this lab we're looking about the spring force and objects attracted to the spring. We use a tracker and glow script to get the model and glow script and the real world data in tracker. Some theories and formulas used in this lab. We use the energy principle and the changes in energy to find the changes in energy, and Newton's second law to model the location of the object, which is the object that is held on by the spring. Some of the formulas that we used, some of the energy formula that we used was the kinetic energy formula, the potential gravitational energy, the potential spring force energy, and also the kinetic and the total energy, which is the sum of all energies. And another formula that we used was also the oscillation formula to find the the spring's resistance. So the spring's stiffness, so that we can find all the numbers correctly. And we use a lot more formulas than these that I have here. Well, here in Tracker we have the object here that's right here, and also our meter stick, which is about 70 meters, about 0.7 meters. And we have our oscillations, and if I run it, we can see that it goes side to side and up and down, and in this wave function. For me, this was my Y was slightly wonky because of my inaccurate readings of doing it. And as you can see, it's pretty much an inverse, a mirror image of each other, and that's what we see. And our Excel sheet, which is pretty much the data that we got from here, is all right here. The A and B, or the A is the X and B is the Y. So we have about 100 data points of of the oscillations of the object that's hanging on the spring. And here's our glow script code. We can see right here our ball the mass of it was 0.402 kilograms. We can find our ball position, which was at 0.1134 meters on the X, and on the Y it was at 0.6341 meters. Our velocity was about 0.298 meters per second, and for the X, and for the Y it's 0.2609 meters per second. And our delta T was 0.21, 1 over the 1 over 210 seconds, so we can have a little more consistent delta T. Our gravitational constant, gravitational force to the Earth's surface is 9.8. Our spring constant that we use this formula right here, which we'll use that, and we got 6.87 for the spring constant, and for the relaxed length of the spring, we use another formula to find L0, which is equal to 0.123. 0.123 meters per second. Meters, I mean. Then to find L, we just find the ball position and the spring position. L hat is pretty much the vector L over the magnitude of L, and S is the magnitude of L minus L0, which is the spring difference, the difference in the difference in stretch or compression. In this case, it's stretch. And then we find our Find the formulas for kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy. Then right here we have our loop for finding each one. We have our forces of gravity and spring, and the force of gravity and the force of the spring, and use some of those to get the net force of both of them. And we use that to find to update the velocity and the positions. And from those we can just update the springs, the spring which is L hat, and spring the spring difference. Then we update our uh, our energy changes, and we find our delta K's and all that. This is pretty much extra. And from here we just have the rest for the code. Running this program, go up. Run this program. We choose our file, which is this one right here. Open it up, and we can see that our spring oscillates the same way as our spring oscillates in tracker. And we have like pretty similar uh, oscillations in the y and x positions, which this is inverse of this one. And after finishing it up, we have our delta K is dissipating. Our potential energy of gravity goes up and down as when the spring goes up, the potential energy of gravity goes up as well. Then our our delta U of the spring will go down. So as this goes up, this goes down, and that's how it was. And our delta K dissipated as for every oscillation that it did, it will dissipating as you can see, like as in the real world, energy dissipates into like heat or other types of energy. So what does this all mean? For my model, the energy principle is satisfied because in the um, in the graph for the changes in energy, we can see that delta E, which is the line in orange, is constant. It's 0, so it cancels everything out. So we know that the energy principle is satisfied because the energy principle states that there's no energy created nor destroyed. It's all converted into different types of energy. So right here we can see that all the energy is 0. And using the equation that I use, which E equals the total energy equals all the different energies combined, you can see it's 0. Using the data that I use in Tracker to find we can find two estimates of the oscillation periods from using the X position and the Y position. So for the X position, we got 1.614 for the X position. Nope. Yes. 1.614, the oscillation of it, seconds per oscillation. But for the Y, we got 1.52 for the oscillation. So we can see that they're pretty consistent by about 0. About 0.1. They're pretty consistent, but we can see that it goes pretty consistently. But the only inconsistencies that they have is that it's from human cause because Hourly didn't actually uh sorry yeah like accurately mark these, because if you can see here, it's not accurately marked at the center. And if you go there, you can go through each one separately. You can see that none of them are marked in a good area. So it's all, like, the majority of it, of the Y direction, is partly to human error, and also that's also dissipating as well. So thank you for listening to my lab report. Thank you.